Hello. As I promised in my message yesterday, I'm going to do a video, The Beginnings of Natural Language Analysis. Natural language analysis is another very large area of artificial intelligence, and it has many applications. I'm not here talking about understanding speech, although that would be the first step if you wanted to apply natural language analysis to speech. But I'm talking more about reading text and summarizing it, or being able to explain what it meant. It would be very useful if we could have some way of meaningfully reading and summarizing so that people could pick what they wanted to read, since the amount of journal material and medical material is huge. Now, there's a distinction between natural language analysis and natural language understanding. Understanding is part of the natural language analysis. Understanding is trying to get at the meaning or to summarize them. There are many, many pieces of NLP. Consider this sentence: the leaves were colorful in October. Well, one easy way to look at it is as a string of words, and that can be very useful. We need to be able to recognize the words. But it's pretty simple to tear apart sentences and turn them into words. You've done that already yourself, probably in some program somewhere. But we want to go further than that. For example, what is leaves? This is called a morphological level. Leaves in this sentence is not a verb, it's a leaf. It's a plural of the word leaf. Were is a form of the verb be. It's a plural form, it's in the third person, and it's in the past tense. Now, these seem like grammatical ideas. They are, and they're important if we wanted to rewrite this in a different way. For example, we'd have to know that the were comes from be. And we might want to relate the leaves to a tree, so we might want to know it's part of leaf. However, to make correct sentences, well, often we have to match these. For example, plural and plural. We can't have plural and singular. But we now need to look at the parts of speech, because that'll help us figure out what this means. So I'm saying the is an article, leaves is a noun, were is a verb, colorful is an adjective, in is a preposition, and October is a noun. Well, that's good, but how can we sort of put this together? How does it fit? Real question is it a correct sentence in our language? Does it derive properly? Is it good grammar? Well, one way to do this is parsing. Now, parsing is frequently done for computer languages. In fact, when you translate, when you hit the button on your C++ to say build, it's parsing what you have and seeing if it makes sense. In Python, it also parses, and then but it does it, I think, more one by one than C++ does, one line by one. Now, here's a way that we might derive this sentence in a grammar of our language. We might say that all sentences begin with the idea that they are sentences, and sentences could be divided, could be replaced by noun part and verb part. That's one way we could look at a sentence. And then a noun part could either be a noun, or it could be an article in a noun, or it could be a few other things too. But for now, we say it's an article and a noun, and we replace the article with the and the noun with leaves. Once we get down to that level, we're talking about terminals. We're talking about words that will remain, that are part of the sentence, not categories we're using to help us put together the sentence. For example, sentence and noun part and verb part. Those are going to be called non-terminals in a minute when I do this more formally. Now you'll notice that verb part can become verb and object. An object can become a preposition and a noun part. And there's lots of looping that could be done in this. The prepositions could keep going. There could be more and more of them. We haven't really finished everything. For example, how does the computer know that leaves are connected to trees? How does the computer know that October is a month? Is this sentence a reasonable sentence, or is it a joke? Suppose I wrote the leaves were beautiful. I left out colorful. I'm sorry. That the leaves were colorful in October. Would I have the same? Would it be the same, or would it be sort of a joke? After all, they usually don't turn colorful in October. I mean, in May or April. So there's a deeper meaning that we really would like to get to. Now, the first thing we're going to look at is syntax parsing. Parsing, if we could have a course called compiler construction. It used to be a pretty standard course in many colleges. And it was how to build a program to translate programs. So like there's a compiler for C++, and there's an alternative is called an interpreter, which goes more line by line, and Python is usually interpreted. But compilers were one of the big software items, and it seems like most the compiler courses don't seem to be that important as they were before. But part of a compiler course was always to write a parser, to take the language and figure out how to determine if the items that you're translating make grammatical sense. And this turned out to be very easy to automate. And you'd get things like parser parsers. That would be programs that make parsers. And they're still around. Now, for example, look at this line, cout, blah, blah, xval. Do you recognize it? Is it a correct line? I say no. The machine would say no, too, because I've used the input symbol instead of the output symbol. So it is not correctly formed. Now, if you want to see how big these grammars can come, I got this from the web. Here's the grammar for Python. I bolded 2 sections there. What that says is statements is replaced by statement as many times as you want. And a statement is either a compound statement or a simple statement. So those are very near the beginning. Then if you look at statement, new line, you look like small statement, command, a compound statement. This thing goes on for page after page after page. I can't even remember how many pages it went. I think I'll use page down instead of what I was using. So you can see it just continues. I don't think we're going to be able to do that for anything right now. But I just wanted to show you that grammars can be complicated. And remember, Python is not a natural language. It's one that's made, and it doesn't have many of the nuances of natural languages. So you can imagine what an English grammar would look like. Now, this whole area of recognizing languages is really at the foundation of computer science, the theoretical foundation, because it really touches on the most important question: what can be computed? We can't say everything. What is it that is computable? When or if you take the theory of computing, which I highly recommend for you, you will be discussing what I'm doing here, in more detail, as not as to be used, but to be seen, to be understood, and then to be used. So, how should we create a model? Models are not meant to be everything. We want the model to be simple. So we're going to take the pieces that are most important to us. We're not going to get into great details. The concept that I'm looking at is called an automaton. It's also called, in the plural, is automata. And there are different kinds of automata. Finite state automata is what I will probably be getting to. Really, that's what it's all about for us. Although there may be some other types too. Now, here's a picture of an automaton. Looks kind of strange to you, probably. The boxes represent states. They are sort of where I am right now, what state I'm in. And the arrows represent input. And every time I'm in a state and I have an input, that takes me to another state, perhaps the same, and I wait for more input. In a sense, I consume the input to move to another state. And one state is designated the start state. That's where you begin to read whatever you're reading. And one or more states are designated as the accept state. In other words, if you reach that state and you're at the end of the input, that's a legally written word or statement or whatever, sentence, shall we say. Now, I added a reject state just to make sure that every single one of the states had something that would show you what would happen, or with a 0 or a 1. But in some cases, we could just say, if you reach a 0 in state S2, there's no place to go, so you failed. Now, let's look at what we've got. That's a pictorial representation. But there's another way to represent it. Before I say that, I just want to use a little terminology. The zeros and the ones are what we're building the statements out of. You might think of them as the words. And the sentences are the strings of the zeros and ones. 0011 is legally formed. Start in the start state, S0. The 0 takes us to S1. The second 0 takes us to S1 again. The 1 takes us to S2, and the second 1 keeps us in S2, and we've finished all the input, and we're in an accept state. So everything's fine. Now, another way of writing that would be to show the progression of states. And these are We're going from S0 to S1 to S1 to S2 to S2. By the way, once you have a diagram like this, it's extremely easy to write a program to do it. It can be a big if-then-else statement or a case statement. And you'll see these kinds of things in networks, in operating systems, many different areas of computer science. Now, another way of expressing and showing a automata is, oh, by the way, I gave you some that did work and some that did not work. So you can look at those. Another way of doing it is to what might be called rewriting rules. The grammar I showed you is a set of rewriting rules. So you can think of this as the grammar of the language. By rewriting, what I mean is that if we have what is on the left-hand side of the rule, we can replace it by what's on the right-hand side of the rule. We can rewrite it. So to do this, we first are going to need a little terminology. The symbols that will appear in the final product, the symbols we read, we're going to call them terminals. So in our case, we have 0 and 1 as the possible terminals. We also need the set of non-terminals, the things that we're using to move us from one place to another. In this particular one, I chose as the non-terminals the names of the states. And I made subscripts because otherwise they might get mixed up with the terminals. So I turned them all into subscripts. Now, we can represent this automaton by this statement, these three statements here. I'm saying that if you have S0, then you can go 0 S1, 1 S1, or 1. So if you look up here, you can go 0 S1, 1 S2, or just 1. And I had to put the 1 in because that's an accept state. Just 1 down there would be an accept. Now from S1, I can replace S1 with 0 S1 or with 1 S2. So if you look at this, S1 goes to 0 S1 or to 1 S1, S2. And S2 can either stay in S2 and go 1 S2, I just keep piling on more 1s, or it can stop with 1. When the right-hand side becomes entirely terminals, we're finished. There's no more rewriting we can do. Because the only thing we replace, if you'll notice, is terminals. Non-terminals. We don't replace terminals. Now that might change with some grammars, but this one, it's only going to be non-terminals for a while. So for example, if we wanted to show that 11111 is in the language, we would say S0 is replaced by 1 S2. 1 S2, we replace the S2, so we get 1 S2. S2 we replace by 1 S2. S2 we replace by 1 S2. Now we have 5 1s. To say that something is acceptable or is in the language, or if it were a computer language, to say that it is a correctly written statement, means that we can get from the start symbol to all terminals and use up everything that came in. Now, if you were asked to describe this language, well, let's see. If we start up here, the first symbol can be either a 0 or a 1. If we get a 1, we only get more 1s. So we can get any length of 1s. We have 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, however many. If we get a 0, well, we can keep getting zeros. We can keep getting as many zeros as we want, because we'll be staying in S1. But the minute we get a 1, we only can have 1s after it. So this language has, let's see how I put it. It's all strings that begin with 0 or more zeros. Now that's a funny way of putting it. I should have said with none or with no zeros or more zeros. And then with 1s or more 1s. It has to have at least 1, 1. Now I wrote it in a way that may or may not be standard. I wrote 0 plus 1, 1 plus. Where the plus means the symbol before it is repeated 0 or more times. So you notice the 0 doesn't have to be there. But there has to be a 1. So I put an extra 1 in to make sure that there's always a 1. Now some people use a 1 prime, I think it is, instead of that. But there's different ways. And that's all I want to say right now. Now I gave you a little homework to do on this. Let me bring that up right now. I built another automaton. It's pretty similar to the other one, but I did put in more arrows here and there. And what I want you to do is show me how you would prove to me that 0, 1 is in this language. Start at S0 and show me how you get to the accept state. So S0, you look at the 0. Where does that bring you? Then you look at the 1. Where does that bring you? Now you're finished. Are you in an accept state? 2, I wanted you to see that 0, 1, 0, 1 is not in the state in language. And you can just look at starting with a 0, starting with a 1. What happens to the 0? Well, there's something wrong here. I'm going to have to go back and fix this because I obviously made a little mistake here. I can't have 2 zeros going. I'm pretty sure I wanted a 1 here. Let me see. I think I wanted a 1 there. 0, 1, 1, 0, 1, 1. Yeah, that's what I was looking for. So I'm sorry. I'll fix that and I'll put that out there for you. Now, show that 0, 1, 0. All right, I'm going to have to redo this homework because it looks to me like when I was doing it last night, I made some mistakes in it. That's 1, and this is 0, 1, 1, and this should be 0, 1. That is in that language. So 0, 1, 1, 0, 1, 1, and 0, 1. So that's in the language. And then try to describe the language. Then write the rewrite rules for it. See what you can do. Don't worry about the reject state. And then write the automaton and the rewrite rules to describe the language that has the strings 101, 101, 101, 101, 101, 101, and so on and so on and so on. So work on that. I don't think it'll be terribly hard, but I hope that it'll be good. We're going to continue getting more into the natural language part of it. This is just the warm-up to see what an automaton does. So I'll see you later. I hope if you started home, you've made it home safely by now. And if you haven't started home, I wish you safety when you do, a safe trip when you do start home. So long now.